changes over time. I'm not going to get into the its and bits of calculus and just directly jump to the shortcuts that you can remember in order to figure out by looking at a graph which reaction order it is. So you're always going to plot a natural log of A. In this graph, or any graph at all, we would have the reactant on the x-axis and the time on the y-axis. And you're going to be plotting the natural log of A, and your calculators are going to give you a slope. So if the graph is linear and has a negative slope, it is going to be a first order. What I mean to say is that you will be given information about a graph. You will be given the x and you will be given the y. And upon plotting that, the natural log of with that information, if you get a linear, if the line is linear, then it's going to be a first order. Upon plotting a natural log of A and getting a curve, it would be the second order reaction. And if you get a horizontal line, then it must be the 0th order reaction. So these are the formulas that you should know about the in the 0th, first, and second order. This equation is already provided to you on the AP formula sheet. From the rate law, you do know that rate is equal to K constant and the concentration of A. What the rate laws, what these expressions really mean over here is that in the 0th order, the rate does not include or does not have any effect because of the concentration of your reactant. In the first order, the rate is dependent on the constant, just like it was on the 0th order, but it also includes the concentration of your reactant. And for the straight line plot, you should be able to recognize that for the 0th order, it would be concentration of your reactant versus time. For the first order, it would be the natural log of A versus time. And the second order, because we use a squared of a concentration of our reactant, please notice how there is a square here. And obviously for the straight line plot, it would be 1 over A versus T. And like I just mentioned, that this is going to be provided to you. All you have to do is replace the natural log of A. T means your final concentration, and O means your initial concentration, the concentration you began with. It doesn't necessarily have to be a 0. It can be any concentration that you began with. Okay, so let's look at what I just meant about the lines when you're going to be using your graphing calculators. If it's a straight line, it's a 0th order. If it's a linear graph, then it's obviously a first order. And if it's curved, then it's a second order. There's another graph at the bottom of it, but I hope that it's if you look into it, it would be making sense in the second order, because the double the concentration as compared to the first is being used. We observe a more of a curve here. Okay, so this is your formula that you will be provided with. For a lot of people who know about calculus would be able to tell that this equation is actually this equation also, a natural log of your final concentration of A over your initial concentration is equal to KT. If you don't know about it, it's all right. I don't know about it. What I use is this formula over here. So let's look at a problem here. How would you be asked a question like this? This is an example question. The conversion of cyclopropane 0.25 molar to propene in the gas phase is a first order reaction. So now I know that this is a first order reaction with a rate constant of 6.7 times 10 to the power negative 4 per second at 500 degrees Celsius. If you look at the formula at the bottom, we can notice that we have quite a lot of numbers to already plug in to here. Okay. What would be the concentration of cyclopropane after 8.8 minutes? So again, we have a question about concentration. You do have your initial concentration, and you also have information on time. So using this very formula, let's see, natural log of your final concentration, which is unknown, minus natural log of your initial concentration, which is 0.25, is equal to your rate constant, which is also given to you in the question. They have to give you information, data about your rate constant and your initial molarity in order to use this very formula. And then because the minutes, the unit for time is minutes, we have multiplied it into 60 seconds. Again, the natural log of A, we just leave it over there. When you plug in the natural log of 0.25, you will get a negative 1.38, and negative becomes a plus. You shift that over there, and on your calculators again, when you plug in e to the power minus 1.72, you would get 0.18 molars. So this was our only part of the equation that we didn't know. How long will it take for the concentration of cyclopropane to decrease to 0.15 molars? Okay, so now the final molarity that we're looking for is 0.15. Our initial concentration is 0.25, and we have our K constant, but we don't know our time. So please try to do this on your own. The answer is already in front of you. It's just the natural logs and everything, and the time would be in seconds. How long would it take to convert 74% of the starting material? So the starting material was 0.25, and we simply needed we simply want to know the remainder, about the remainder of it. So as you can see, we have the AT left over here. I'm sorry, I forgot loading LN. Okay. And if it's 100 minus 74, you're going to get a 26%, because we want to know what is the remaining 26% off 0.25, because 74% is gone. Okay. So again, you would plug in all the information and you should be getting a similar answer. Okay, so we talked about this in class, a very interesting general information about half-life. So I'm just going to skip this and jump to a problem about half-lives. Okay, so the way it's in the name, half-life is basically, half-life is basically, how long it's taking for that thing to be half. That is what it really means. So if you had 100 grams, for example, how long is it taking to go down to 50 grams? If you have 100% of something, how long is it taking to go to 50%? Let's look at an example over here. If you start with 120 grams, a gram sample of radium, how much will be left after 44 days? Calculate the percentage left. This is a very random example. Maybe you will not be asked about this, but not a question about grams and percentage, because we are usually asked about concentration. So you have been given the half-life of radium, which is 11 days. So what we need to know is that radium is going to decrease by half no matter how much amount you have of it. It's going to decrease into half in 11 days. A lot of things would decrease into half in 10 seconds. A lot of things would decrease into half in 100 years. So it varies. For radium, the half-life of radium is 11 days. You guys must have heard of the term shelf life. that how long can you keep something in the refrigerator for, or if you have a medicine at home, we do know that it has an expiry date, but if you have opened up something, how long is it going to remain, edible or usable? So that is what we call something having a shelf life. A similar way, every like molecule, element, all of these things have a half life, not a shelf life, obviously. So it's just like half of what you have. That is why the formula is T half. Okay. So if the half life of radium was 11 days, how much will be left after 44 days? So the half-life of 120's half is 60 grams. So that is one half-life, which I have colored over here. The second half-life would be the half of 60, which is 30 grams. So that's your second half-life. Going from 30 to the half of it would be 15 grams. That is your third half-life. And going from 15 to 7.5 is another half-life. So a total of 4 lives. Okay. And if you wanted to calculate the percentage out of this, see how 44 days is actually 11 days, like 4 times. So that means 4 half-lives. That's why I didn't go lower than 7.5, but I could have, depending on, how much I'm supposed to do. And if I wanted to do a percentage of it, so it's happening it's 4 half-lives, so I'm going to go 100, 50, 25, 12, and 6.25. If it was 5 half-lives, then I would have gone obviously lower, the half of 6.25. Okay. Now, that was a very, very basic example of how you would calculate half-life. Let's look at how this question is given to you on AP Chem. It can be as simple as the example I just did over here. I'm going to zoom into it. Okay. So here I have, when I counted, it was 16 molecules. And I noticed that per minute, the 16 is going to an 8, and a minute later, it's going to 4, and a minute later, it's going to a 2. So the molarity is going down, is turning into its half at regular intervals. This is how I'm sure, on the basis of observing a irregular interval of change in molarity, that this is a first order reaction. Here for half-life is that the half of that time is your half-life, and the half of your initial concentration is the half-life concentration. Let's look at an example over here. The decomposition of methane C2H6 to methyl radicals is a first order reaction with a rate constant of 5.36 times 10 to the power negative 4 per second at 700 degrees Celsius. We don't have anything we're not going to be using the temperature here for this formula. And for these half reactions, the K constant is 0.693 over half-life. There is a reason why it's 0.693 over half-life, and it has to do with the natural log and everything, but I don't want to get into how we got this. It is on the notes that I've given you, but again, it's unimportant because this is the only half-life that you should be concerned about. Second order half-lives are never asked they're never on the AP test. So let's see over here. So we're meant to calculate the T half. So we just wrote the T half here, 0.693 over K constant for any kind of first order reaction. It's telling you that it's a first order reaction. If it hadn't told you, you would have just looked at the graph or your data, and it would have told you what kind of reaction it is. And in order to calculate half-life, it has to be a first order reaction because that is what you're expected to know. So for the K constant, because they have given us a value for the K constant, we just plugged in all the numbers, and after you calculate all of that, these are the seconds that you get, and you simply converted that to minutes. I hope that this equation is making sense to you about half-life, and you would be able to associate the formula for K constant for half-lives, and I don't think you need to know anything more at all in order to solve questions for these.